Right, you can go ahead. Thank you.
Okay.
Thank you,
Well,
Mario.
thank you for having me. And I hope online people are hearing me well. So you said I changed path a little bit, but this is actually a machine learning talk, okay? And that's a change of path within machine learning. So when I was talking with Mar earlier, she was telling me, I was surprised you're not doing machine learning anymore. But no, actually, this part here is the machine learning part, right? And that part is the astronomy part. So I will be talking for a solid block of minutes on machine learning. Just it's a different kind of thing than what you might be used to if you heard about like the usual deep learning stuff and so on. And so if I'm moving on, yeah, on the first slide, we start like immediately talking about machine learning. You know this guy? Ever seen this guy? This is Judea Pearl. He was the Turing Prize 2012. And he started the big like discussion when he said, yeah, guys, you've been nice with this machine learning. You had fun, but it's all just curve fitting, right? So as you know, like there's been lots of interest in machine learning recently. And to say it's just curve fitting is a bit, you know, it was very controversial. But this problem, I mean, he's actually saying something true. And this problem is going to become our problem because in astronomy, like I'm saying in astronomy, I might say in astrophysics, right? Like we're all in and around that field. Now, like when I walk around and I talk to people and I say, hi, what's up? Yeah, what do you do? My job is to apply machine learning to astronomy or to bring machine learning to astronomy or to do astronomical data analysis with machine learning. And I believe that in 5 years or 10 years, we will be just saying, I'm doing astronomy, but we will be doing this stuff. So we will be taking spectra or astrometric data or whatever it is, and rather than just like clicking on the star scenario or whatever, we will be doing convolutional neural nets, autoencoders, this kind of stuff, or something like even more advanced, right? So then if machine learning is just curve fitting, meaning that there is no understanding in there, it's our problem because we want to do science, right? So we want to figure stuff out in a way that people can understand in our human minds. And it's a big problem that data-driven methods, very often by data-driven methods, I'm putting in the bucket of data-driven methods all the stuff you're probably familiar with by now, like neural nets, support vector machines, random forests, so that kind of stuff for supervised stuff, and unsupervised like clustering and dimensionality reduction. All this kind of stuff is data-driven in the sense that it's very flexible methods that do not build on strong hypotheses like we do when we do physical modeling. And they often produce black boxes. What does this mean? It means that sometimes you got the neural net to tell you this is spiral galaxy and this is an elliptical galaxy, or this is the spectrum of an AGN type 1 and this is type 2. And you're like, yeah, okay, but why? You have to believe this stuff, or do you want to actually figure out why the machine is telling you this? So that's a big problem we're facing in astronomy and in science in general. And there are different ways to get out of the black box, let's say. So there's a whole field of machine learning interpretability and explainability, which are two related but different concepts. The idea is to build models that can be explained so that I can tell you why the machine did it, or that are uninterpretable, understandable from the ground up. But one big ingredient in this galaxy of machine learning explainability and interpretability methods is causality. So what do we mean by causality? It's such an important thing. Well, before getting philosophical about causality because it's a topic that lends itself to lots of digressions. Here's a bunch of literature. Like if you want to get into causality from the statistics and machine learning side, there's this seminal book, which was like, it has a second edition, 2009, but it came out in 2000 actually. And there's this other seminal book, which was 2001, I believe. If you read one of these two, you're basically seeing what the state of the art of causality right now is, at least at the elements level. And then there is a great course from this guy, Brady Neal, that was at Milan, not Milan, where I am now, but Milan, which is an Institute of Artificial Intelligence in Montreal. So, I mean, it's related to Université de Montréal and so on. And this guy has a great course in this. So let's get philosophical then. What is causality? What does it mean that A causes B? So we believe that we know this already, right? And at some intuitive level, we think we know this. There's like, here I was just collecting a bunch of different quotes from texts that are very, very different from different times and different places. And people are basically saying, this guy is an experimental psychologist, is saying like, that people, when they see two balls bouncing on each other in a certain way, they just immediately click and they say, this ball caused the other ball to move. And this is like a mystical text from the Middle Ages in China, and it's saying the same thing as this guy. So it's probably something that you can get at through experiments, but also through introspection as well. But in science, we tend to want something more precise than this. We want not just intuition, but we want a clear definition of what causality is. We want operational definitions, meaning that we want to know what to do. So we want to know how to follow a series of steps so that we can say, this thing causes that thing. So if I say the chicken weighs 3 ounces, it's because I can do this operation where I put the chicken on the left side, hoping that the chicken doesn't move too much. And I put these 3 things on the right-hand side. And I'm like saying, okay, that means it weighs 3 things because it's not leaning on either side, okay? So we want something similar for causation. But what people tell us about statistics when they talk about causation in statistics is usually in the negative. People say causation is not implied by correlation, right? So you probably have seen this, it's very funny, but the thing is, usually for a century, since the birth of statistics as a science, people have been saying, don't trust correlation to tell you that you are seeing a causal relation. There can be correlation because something else is causing 2 things, and then those 2 things correlate with each other, and this is called the confound pattern. More generally, you could have reverse causality, or you could have other effects that give you a correlation in the absence of direct causal connection between quantities. But if we want to build an operational definition of causality, this is the raw material we work with. We have a ton of variables. We see which ones correlate or depend statistically on each other. So here I'm writing statistical dependency, but you could say correlation if you're in a linear setting. It's a pretty similar notion as long as you find yourself to linearity. So if we have a bunch of variables, we can do something, even just starting with correlations. That's the great new thing that started this field of causality. So we can come up with ways to tell that A causes B from a bunch of correlational patterns. So as an example, like an intuition pump for this thing, here we have 3 variables, y, x, and the color, right? Which we can call z if you want. So here you see that x correlates with y, because I put the dot that x correlates with y. X correlates with color. So on the right, the points tend to be bluer, and on the left, they tend to be redder. I hope this is colorblind friendly. The website told me it is. Okay. And y also correlates with color. Like you move from the bottom to the top, it's getting bluer, right? If I control for y, so I'm looking only at points in a narrow window around a certain value of y, looks like all the points end up having more or less the same color. So holding y constant, x is not correlating with color anymore. If, on the other hand, I hold x constant, oh, it looks like at this point is reddish and that one is bluish. So it looks like that holding x constant does not have this effect on color. So y is still correlated with color. So can we leverage this pattern for causality? Well, we can come up with a piece of what will later be a definition by saying that if I have three variables, and as an intuition pump, as I was saying, let's think about concrete stuff, like it's cloudy, so how many clouds are there in the sky? It rains, how much rain is coming down, and is the grass wet? So I can measure how wet it is by looking at it. So these three variables behave like that, meaning that if I don't know, I'm not looking at how much rain is pouring down, I will see that there is a correlation between the clouds, how many clouds are in the sky, and how wet the grass is. Because, I mean, typically when it's sunny, it doesn't rain, right? So there's no clouds, and this tells me something about the wetness of the grass. On the other hand, if I know how much rain is coming down, then I'm done. I don't need to look at the clouds because I know that it's the rain that is making the grass wet. Okay, so if I have variables that are correlated like this, but controlling for one of them breaks the correlation with the third one, this suggests that there is a chain of causation in this way. By suggest, I mean we can use this as a definition downstream for causation as part of the definition, because then we need another ingredient. Here I have another example. I have variable u and variable v that do not correlate with each other. So these little dots are all over the place. There is no line. I mean, you can draw a line. If you fit u as a function of v, you will get a line like this. If you flip it over and fit v as a function of u, you will get a line like this. There is no correlation, or at least it was intended to have no correlation when I put down the dot. On the other hand, you see that size changes in such a way that increasing x increases size, and increasing u increases the size, increasing v decreases the size. If I were to take the average in u, I would see that as v increases, the average size is increasing, and I would get also dependence if I did the same by taking averages in u. Also, here, as you can see, if I control for size, if I take only balls of intermediate size, these ones, I will end up having a correlation between u and v. So if there is a pattern like this looks like having the grass that gets wet, which is size, and sprinklers, so artificial way of making the grass wet, being active, this could be u, and raining could be v. So in principle, I can turn on the sprinklers independently of the rain. So they could be on when it rains, when it's raining, they could be off when it's raining, it's up to me, right? So there is no necessary connection between sprinklers and rain, and I can think that in the wild I would see no correlation between sprinklers and rain. We know that people usually don't do that. They don't water the grass when it's already raining, but like, let's go on with the metaphor. I will find a better one at some point. The thing is, since these two things were independent on each other, u and v, sprinklers and rain, can like both coexist with grass being wet. It's weird to think that grass being wet causes both the sprinklers and the rain, and sometimes it causes the sprinklers, sometimes it causes the rain. So we could use this thing, this joint effect idea, to build a whole definition of causality that goes like this. So we got a correlation, A correlates with B, so it's always there. Like no matter where I look today, I look tomorrow, I always find that rain and grass that is wet, they go together. There are no roofs in this world. Okay. Then there is something else that correlates with both A and B, but in such a way that if I control for A, this something else is the clouds, then this thing does no longer correlate with the outcome that they care about, the grass being wet. And then there is also something else that correlates with the grass being wet, but is independent on A. So I put them together in this plot here. I'll go back to this later. Essentially, I can define that pattern of correlations to mean this, to mean that D causes B, A causes B, and C causes B through A, okay? So this is and then this notion is at the basis of a bunch of algorithms that do this kind of exercise of defining causality from correlations. And this is based on conditional dependence and conditional independence of variables. So these kind of methods are called constraint-based causal discovery algorithms. This is a branch of machine learning, so it counts as machine learning, but it's different from most of the rest of machine learning, right? Even though it has strong interactions with it. Notice that people call it causal discovery, but from my point of view, it's more of a causal definition, meaning that if you say discovery, you mean that like metaphysically causality is there somewhere up in the sky, but I'm not really a fan of that point of view. So here we can say as scientists that we are defining causality through these patterns of independence. And there's a bunch of algorithms that do this like kind of exercise called, like the most famous is the Peter Clark algorithm. And you can look it up and see how it works internally. It leverages this kind of thing. So what these algorithms do is that they turn a bunch of variables. So initially you have a bunch of variables that are all measured, so sampled. Essentially you have, I don't know, the height of a person, the weight, the length of the hair, the color of the shoes, I don't know, a bunch of things like that. And you put them in a nice matrix. You have tabular data typically. And in this nice matrix, you have like your columns are different variables, and you can tell whether there is a correlation or not between variables, right? And from that, you get these. So you get a guess at how the variables cause each other, which is quite interesting. And we represent it as a DAG, directed acyclic graph. So every variable is a node in this graph, and every edge is potentially oriented. So it should be oriented, directed, so that you have a real DAG, but we will see there are other diagrams that don't orient the thing, so they don't have an arrow necessarily between each other. And those edges mean a relation or lack thereof between variables. In particular, here there is a lot of relations that are missing. So you don't see a relation between A and D and C and D, and those carry information as well by not being there. Okay, there are also other methods to do this job. And in fact, the practical methods are of this kind, but it's easier to explain, I think, the methods I just tried to explain. And essentially, you can, given 4 variables in this case, for instance, you could be listing all possible DAGs. So all possible causal structures, all possible lists of causal relations between these variables. So you would have one where all the variables are disconnected, one where C causes A and nothing else happens, one where B causes A and nothing else happens, and so on and so forth. So you look at all of them, and it's a lot of DAGs. Even for 4 variables, it's already a lot. For 3 variables, it's 25. And you score them based on how well they reproduce the joint distribution, the one that you have sampled, under certain assumptions. So you can assume that whenever there is an arrow pointing from C to A, it means, for instance, that A equals a constant times C plus some Gaussian noise or stuff like that. So if you do this, you get a way to score the diagrams and say which one is more likely to be the real causal diagram that underlies your physical mechanism. And then you look at the highest scoring DAGs and try to interpret them. Okay, this was nice, but what about astronomy? Yes, we will be getting there at some point. These are the mice galaxies. That's why the cat is looking at. Okay, what about astronomy? Yeah, right. I just got the paper accepted in APJ, and with this student, and I was co-supervising him. And this paper is the first like serious application of causal discovery to astrophysical data. And it falls right, like we say in Italian, il cacio sui maccheroni, like the cheese on the pasta. No, it's perfectly aligned with what the community needs now, I believe, because you know that there's been lots of talk about co-evolution of supermassive black holes and galaxies, right? And coevolution means I don't know which causes which. Like, is it the black hole that causes how the galaxy evolves, or is it the other way around, right? And here, what we're doing, like it's been like 25 years, people are arguing about this. What we're doing is taking a bunch of data that were assembled from this guy, and trying these causal discovery methods on them. If you balayé the QR code here, you open the window. The bottom line is that we took some galaxies. Hello. These are come in different morphologies. I know everybody's probably an astrophysicist here, so you know it. But the point is that we will be looking at a sample of mixed morphology. There will be ellipticals, there will be spirals, and there will be also lenticulars in the middle here. And all of these galaxies have a supermassive black hole in there. So you had the picture of in your office. Nice picture. It is the variables we took for every galaxy in the sample. The sample is 101 galaxies, so it's pretty small data. So we are in the era of big data, but this is small data actually, because you can do cool stuff with small data too, even like with these new methods. About 100 galaxies, of which 35 are ellipticals, 38 are lenticular, and 28 are spirals. So it's evenly broken down by morphology. And we measured a bunch of things. Measured means here collected from the literature. And for the data, you can ask this guy, who's the third author there. He's been doing the collecting of the data. So the black hole mass, the velocity dispersion of the galaxy, central velocity dispersion, that tells you about how pressure supported the bulge is, right? What the stars are doing over there, the velocity dispersion. And you get the half light radius of the spheroid, which is the whole galaxy in the case of the ellipticals, and the projected density. So these three variables, you probably know that they constitute the fundamental plane of galaxies. So they are bound by a three-way relation. Then we took the mass of the galaxy, the total stellar mass, its color, and the specific star formation rate. Why these variables? Because they are probably those that afford a better view into how the galaxy is nurturing the black hole and making it grow, right? For instance, if the black hole has some feedback, it should affect the specific star formation rate, because the AGN feedback might heat up the gas or kick it out, and so you would expect an effect on the star formation rate. On the other hand, these three variables are connected with each other, and we know that the sigma has a strong correlation typically with the black hole mass. So there is the mass black hole sigma relation, which is very, very low in intrinsic scatter, and people are wondering what exactly creates this relation. And the question we're asking on this data set is, what causes what? Can we tell that the mass of the black hole is causing, for instance, the velocity dispersion, or the other way around? So we threw the data into this causal discovery method based on scoring the diagrams. And the result we're getting is this, which is interesting because it differs across morphologies. So we're getting that elliptical galaxies appear to have the properties of the galaxy, in particular the velocity dispersion, to cause the massive black hole. And we find the opposite direction of causation for spiral galaxies. Interestingly, though I'm not writing it here, but it's in the paper, lenticular galaxies, which are morphologically in between, appear to be in between here as well. So to have more difficult to determine direction of causation. So if I go around like in the US, where you need to be a bit more arrogant, right? I'm saying we solved the problem of causation. Like we know what the direction of causation is. Here in Europe, I can say, well, this is a step toward that. Criticize it, please. Okay. What we find, this is for ellipticals more in detail, that the end result of this kind of algorithms is DAGs, directed acyclic graphs, as I was saying. And we look at the most frequent ones. By frequent, I mean that we're sampling from the posterior, right? So we get structures like this. So this is the massive black hole that I was underlining in green. And stuff is causing it. In particular, velocity dispersion is causing the massive black hole. And here and here. If we move on to spirals, we get the opposite thing. So these are all equally plausible causal structures where you get that the black hole mass is causing the velocity dispersion, except here. Then if you move on to lenticulars, you typically get something in between. So there's a bunch of stuff causing the black hole mass, but then the black hole mass is causing typically RE, the half light radius. And interestingly, the whole star formation and color group of variables is on the side here. We didn't understand why in lenticulars. Now you will be asking a question here, I think, but I can ask it for you. What are these numbers? Okay, so keep in mind that the space of all possible DAGs with 7 variables, 1, 2, 3, 4, 5, 6, 7, is big. So there's this number of objects. So these are all possible graphs with directed edges between 7 variables. It's a big number, the reciprocal of which is 10 to the minus 9, basically. So there is one probability in a billion that you extract a random DAG and you get this one, okay? When we look instead of the posterior probability, so after we run the score-based algorithm that is doing this selection of the DAGs, what we get is that 0.2% of the probability mass is on this DAG. So we change from 10 to the minus 9 to 2 times 10 to the minus 3. So it's a big change. It means that these guys are very, very favored to be the true causal structure. Same here, you get a similar thing. Sorry. Yeah. So, why? Oh, good question. It's because of this thing in the bottom here. So when we are doing this causal discovery, we are agnostic to structures, to differences in structure that are indistinguishable based on conditional independencies. And these 4 structures, for instance, all correspond to a class of equivalence over DAGs, which is called Markov equivalence class. And it's summarized by this thing. You see here, there is no directed arrow. So essentially, you can have that arrow directed like this or like that. And also here, there is no directed arrow. It means that these guys are all equally probable under the score that we are using, because they don't entail differences in the way conditionally independent, in the way variables are conditionally independent on each other. So those operational definitions that I was like covering before cannot distinguish between the guys. So it's all right that they should have exactly the same probability. Yeah. No. So the prior probability is very small, right? So it's very unlikely that you get this DAG just by fishing one at random. If you take into account the evidence from the correlational structure, the actual correlational structure of the data through the causal discovery method, you get a posterior. And the posterior is much bigger. So this DAG is, if it comes out at random from the posterior, is going to happen 2.4 times out of 1,000, which is low, but it's still much bigger than 1 in a billion. Okay, so essentially, we can take a look actually at the whole posterior here. So here I'm showing the posterior probability of a given DAG as a function of the rank in probability of the DAGs. So all the DAGs are these nice little plots here, right? These directed cyclic graphs. Each one of them has a score, which is the probability in the posterior. And you see that, for instance, take the E ellipticals. You see the blue line? These are the most frequent DAGs, the first four. It's the horizontal segment of the line here. Then you get the next class of equivalence, which is less likely, and then less likely, and so on, until it drops off. And you see that I can cover a lot of probability. So I have a knee in this curve, in the blue curve, at about 10 DAGs. So 10 DAGs are covering, I mean, I don't know, it depends on how you decide where the knee is. You could use 1,000 DAGs and cut it off here. But it's a very limited amount of DAGs all over the totality of them. And also here you can see in the blue, purple, and green line, I think it's brown, it's not. There, I'm showing you the distance between the DAGs. So whenever I go from this one, for instance, to this one, here I'm flipping an arrow, right? So this is the same, and I got this arrow flip over here, or rather, in the display, it got the variables switched, but it's the same as flipping this arrow. So that's one character distance. Is like two words that are like pair and bear, okay? Just one change apart. And that's the Hamming distance. So as you move away from the most frequent DAGs, the Hamming distance goes up a lot. And it's telling you that the most frequent DAGs are all similar to each other. So the Hamming distance is quite small here. And then if you go to unlikely DAGs, then they're all different from each other. And that's telling us that the causal structures that are privileged by the posterior are similar. So we're not seeing a situation where we have two competing theories. One is telling us A causes B, and the other one is telling us that F causes G, and they are both equally likely. We were lucky. Basically, we got a situation where we can tell that there is one dominant theory, one dominant family of DAGs that all look similar to each other. Another exercise we can do, since we have a probability distribution over all the DAGs, we can count how many times, weighing them by the posterior probability, you get an edge that points from one variable, for instance, sigma 0, to another variable, for instance, the mass of the black hole. So here we look at elliptical galaxies, and in the DAGs of the elliptical galaxies weighted by the posterior, we get that 78% of the times it's the velocity dispersion that causes the mass of the black hole. If you move towards the morphology of the spirals, if you go all the way to the spiral, it's only 22% of the times that you get this, and the reverse direction grows to 62%. It was 19% here. You may be wondering why they don't sum to 1, because in some DAGs there is no connection, so that is not shown here. So here I'm essentially, this number is counting how many times there is an arrow, like in the space of all the DAGs weighted by the posterior, how many times there is an arrow pointing like this, rather than an arrow pointing like this. So it can go from velocity dispersion to the black hole mass, or you can go from the black hole mass to the velocity dispersion. We can average them, and we get these plots here. And we see not just the relation between the black hole mass and the velocity dispersion, but another interesting thing is that we do pick up on the fundamental planes here. And we could potentially start talking causality of the fundamental plane, which is a bit trickier because the fundamental plane is the virial equilibrium, basically. So it's weird to think that the virial equilibrium has a causality direction, right? So we didn't get into that for now, but it also picks up some signal here, like when changes from one variable, one morphology to another, because spirals don't have fundamental plane, right? Yeah, question? No. I saw a hand. Okay. So there is a physical interpretation for this stuff. It's a qualitative one for now, but we're working on making it quantitative with simulations. And in the paper, there is some work done with SAMs, so with semi-analytic models, but to use full-blown simulations would be better. So anyway, the idea is simple. Spiral galaxies have gas, right? So gas is mediating between scales. So the black hole lives on a very small scale. It's like, no, black hole the size of the Earth would fit in my hand, right? So this is not the size of the Earth, it's much bigger, but still, it's very small scale. On the other hand, the galaxy is on an enormous scale. Gas is mediating because it's like being pushed out by jets, and it's then responsible for star formation. So in spirals, you have gas. In ellipticals, you don't, because the gas is being used, right? On the other hand, ellipticals are made, well, that's what we believe, right? Generally in cosmology, the consensus is that galaxies, spiral galaxies are formed by merging, iterated merging of spirals and other stuff. So what happens is that the properties of the galaxy, of the smashing spirals that end up building an elliptical, determine whether you have a merger or not, meaning that they determine your cross section, right? Whether you're going to be captured and you end up merging or not. And those properties correlated with the mass of the black hole in the spirals and determine how you end up merging the black holes to create a supermassive black hole through the mergers of the galaxy, right? So it kind of makes sense that in spirals, you just have like basically the galaxy is still sitting there, sort of, and the black hole is growing and it's affecting the gas, and through the gas, the star formation and the velocity dispersion and so on. When you think in terms instead of mergers making up ellipticals, it makes sense that the properties of the galaxy that drive the merger, because it's like being in a car crash and I have the wallet in my pocket, but the wallet is not driving the car, right? Even though there is the driving license in there. So this is an attempt at a physical interpretation that is somewhat satisfying for now. Okay, so if you want more details on what's going on here, well, I made the 45-minute mark perfectly. You can take a look at this works. The latest one is this one, where we're using somewhat newer methods of causal representation learning. And this was presented at New Rips in December this year. And that one is the paper, like the main paper. This is another talk. If you like my voice, you can click this one. It's at Perimeter Institute. And then here, this is the very first paper that was published. Okay, so I'll be taking questions or not, depending on you. Okay. Hi. So, like the honest question answer is that I don't know, because we have a small sample. So for now, it was like already challenging to break it up into 3 parts, right? You have 101 points, and so basically what you're asking might be solved by doing some binning of the lenticulars and saying how elliptical or how spiral they are, and looking whether they behave differently. Yeah, if the limiting factor here is having the masses of the black holes, right? Potentially you have a ton of galaxies, but the ones with a good measurement of the mass of the black hole is limiting the number of data points we have a lot. And as a result, it's hard to answer that question. But let's work on it. Oh, we could even like just not use a number. We could just use the variable, the categorical variable. To flip. Mm-hmm. Yeah. Uh, but what you, I mean, if you were just to not have that variable, but just throw all the galaxies into one bucket with the 7 variables, then you probably would end up with two theories, right? If you add that variable, you should be able to get a causal structure. That problem is that it's a weird variable in the sense that it's modulating the interaction of other variables. It's not directly acting on something. It's a bit tricky. Definitely not linear, but it's even like I don't know. We didn't try. That's something that we could do, like throwing in this variable and seeing if it makes sense, right? Yeah, we didn't do it yet, but and there's so much stuff we could do. Yeah, yeah, exactly. I mean, like it's a great question. So, like this question is basically the whole field of causal representation learning, right? So in our case, we were just like picking the variables and calling it a day. But how do you know? Like, how do you even know that you should be using like even these variables? You know, the fundamental plane, they could be just turned into some other variables just by doing some linear transformation, and they would still be the same thing, right? So people can like build a mass for the thing or virial ratio or something. And why stick to this stuff? We don't have a good answer for that. A good answer, we we're like trying to, to work towards it in the last paper in this one. No, sorry. Not bad. In the causal representation learning one. So essentially, we're we're taking this data set of variables, so still sticking with these ones, but then looking at linear combinations of these variables, doing independent component analysis. You probably know what it is, but for the people who might not know, like essentially you might have heard about PCA, principal component analysis, right? And that is a way to optimize, like it's a rotation in the space of your variables that picks out axes of maximum variance, right? but you can do a similar thing when, but trying to maximize something else. For instance, non-Gaussianity. So the reasoning is that if you have a a variable that is a linear combination, so essentially sum of different variables, it should be more Gaussian because of the central limit theorem than the native variables that may have whatever distribution they want, right? So if you try to maximize non-Gaussianity, you are getting closer to the original variables that are not getting mixed with each other through linear transformations. This is heuristically. So ICA, independent component analysis, is trying to do something of this kind. It's similar to PCA, but it has this different objective. And by doing that, what we're finding is actually pretty cool. The paper is this one. This one, yeah. So you can take a look at it on the archive. Essentially, what we find is that we are doing ICA on the variables that are not the mass of the black hole. So on the fixed variables, all the variables minus the mass of the black hole. And if you have a causal structure like these, wait a sec. If you have a causal structure where you have a dog, I don't know, it looks like this. So you have that the mass of black hole is the joint effect of a bunch of other variables. Imagine that you take all those variables and you do this game of ICA, which intends to produce independent variables, okay? So then independent variables may have a joint effect, but they cannot have a common cause. So this structure suggests, once you do your ICA, that there could be more than one IC, more than one independent component that is causing the mass of the black hole. But if you have the opposite structure, like this one, okay, once you do your independent component analysis on the variables, you cannot have multiple independent components that are both caused by the black, right? But they cannot have a common cause because of Reichenbach's hypothesis that if you correlate, you either have a common cause or A is causing B or B is causing A, right? And then that's exactly what we get. When we do the ICA, in one case, we get that only one IC is connected to the black hole mass. And in the other case, we get that multiple ICs are connected to the black hole mass. Maybe I can actually open the paper, but I don't know, tell me if it's too late. Yeah, 2 minutes. Okay, so there we go. So yeah, I could show you. It's not getting out. Okay, now it's getting out. I could show you a slide from the paper. And this was like presented to the last new RIPS. Here it is. So we are getting what you expect, basically. So, and we were very happy when we found this because it means that the whole analysis is kind of robust. This is the stuff you know already. Here it is. So in the ellipticals, these are the independent components of the variables. And you should be able to see the mass, where is the relation with the mass of the black hole. Yes. Wait a sec. Here, yeah, this is the most enlightening thing. So the number of independent components is different in S0s, in E, and in S galaxies. And if we look at the correlation with the correlation coefficient here with the mass of the black hole, here for ellipticals, we're getting basically two variables, two independent components that are correlating with the mass of the black hole. And here for spirals, it's just one, this one. Okay, so it's suggesting that the causal structure is actually that way. Yeah. I don't know. Yeah. I mean, like, it's hard to give a probability to that risk, like, but what we saw is that if we take a subset of the data set we have, we're still getting the same result. So it's a different direction, right? So we're getting even fewer data points and testing that it's still giving similar results. This should be in the paper. Of course, who knows when we get like 2 million galaxies with black hole masses measured and so on. It might even be that we are looking at a biased sample here, right? So maybe it would generalize, but we're unlucky that the ones that are near us, we can see with our instruments now, are peculiar. So, well, let's see.
People online, do you have questions? There is one.
There is in the chat. Here's the YouTube link.
So, if you have more questions, can ask. Let's back again.
You just close the Zoom?
Yeah.
Oh, okay.